You know how a chameleon can move its eyes all over the place in almost any direction? Well, the reason why is a biological marvel. But what if there's an even deeper secret hiding inside? That's what we're looking at today, the chameleon's secret helix. Okay, so it all kicks off with something pretty simple. You look at a chameleon's eye and you notice how incredibly mobile it is. The nerve that connects that eye to the brain? It's not a straight line. It's this tightly wound coil. And that immediately makes you ask, why? Why that shape?
Well, there's a simple answer, at least at first. It's basically a spring, like an old telephone cord. That coil gives it a ton of slack, so the eye can swivel all over the place without stretching and, snapping that delicate nerve. That part, that's solid, well-established science. But this is where things get really interesting. See, a new theoretical paper is throwing a curveball. It's asking a much, much stranger question. What if that coil isn't just a spring? What if that very specific shape gives it a secret second job?
Right, so a nerve's secret second job? The whole idea is that there might be a hidden optical function here. The proposal is that this nerve isn't just sending electrical signals like we thought. No, it might also be interacting with light itself in a really, really sophisticated way.
And the author of the paper, Ido Margolin, puts the question perfectly. He asks, does this geometry also support optical waveguiding or useful delay effects? In other words, could this specific coiled shape actually be guiding light waves, or maybe even creating these tiny, incredibly precise time delays in the signals? Okay, to really get this, we need to talk about a concept called a topological waveguide. Now, don't let the name scare you. Just think of it like a water slide, but for light, right? It's not the plastic of the slide that matters so much as its twists and turns, its shape. And the hypothesis here is that the physical shape of the chameleon's nerve, that helix, is basically designed to do the same thing, guide and manipulate light. So, let's put this into perspective. A standard optic nerve, it's basically a straight shot, an electrical conduit. Pretty simple. But the chameleon's optic helix, yeah, it sends signals, but its coiled form has led to this absolutely wild hypothesis. Could it also be acting as an optical delay line, a component that actually slows down light with insane precision? Now, look, that is a huge claim. So how on earth do you even test something like that? Well, the paper proposes this really brilliant approach. It's called design to falsify. And instead of trying to prove the idea is right, which is what you might expect, the entire experiment is designed to prove it's wrong. That right there is the mark of some serious scientific thinking. And the very first test, the first hurdle they have to clear, is the most obvious one. Think about it. The optic nerve is tucked away behind the eyeball. So for it to do anything with light from the outside world, that light has to somehow get through all the tissue in the first place. This is ground zero, the first and most critical test. So they've designed what they call the A0 go, no-go test. The principle is actually pretty straightforward. You take an ethically sourced, non-living chameleon sample, you shine a very safe, low-power light at the eye, and then you stick a super sensitive detector right where the nerve would be. The whole point is just to see if even a whisper of light, any signal at all, makes it through. And it all comes down to one make or break number, 6 decibels. That's the magic number for the signal-to-noise ratio. Now, what does that mean? It just means the light signal they're looking for has to be noticeably stronger than all the random background noise. If they can't get a signal that's at least 6 dB clear, well, the biological theory is toast. It's considered falsified, and that whole line of research just stops right there. But, and this is maybe the cleverest part of the entire plan, what happens if the test fails? What if no light gets through? The research doesn't just die. No way. It pivots. It goes from studying biology to creating an engineering blueprint. The next step is to create what's called a synthetic helix sleeve. It's this tiny 3D printed coil made from a tough, biocompatible material from plants, and it's designed to perfectly mimic the shape of the chameleon's nerve. They can then wrap this sleeve around a normal glass optical fiber. So you see what they're doing? They're copying nature's design, even if it turns out the chameleon itself doesn't use it for this optical purpose. It's pure bioinspiration. So why is this so cool? Because that shape, that helix they copied from nature, has massive potential in engineering. We're talking miniature optical delay lines for tiny circuits, biocompatible sensors you could coat with living cells, advanced parts for optical computing, you name it.
The design has value whether the chameleon uses it that way or not. It's a win-win.
Okay, so where is all this headed? How does this build to something even bigger? Well, this research isn't just about one little component. It's pointing towards a much grander vision, a future that honestly sounds like something straight out of science fiction: living computers. The paper even introduces this new concept called the tau kernel. The best way to think about it is as a topological timing gear. In this future vision, the physical shape of the helix isn't just a passive little guide. No, it's an active component. It becomes a fundamental building block where the geometry itself creates those precise time delays. That's a core function for a completely new way of computing. So you see, when you pull back, this story isn't really just about chameleons, is it? It's a stepping stone. It's a first step toward a whole new field that the paper calls biotopo computing, a world where we actually learn from nature's weird and wonderful shapes to build technology that solves problems in ways we've never even thought of. And that leaves us with one last kind of mind-bending thought. We're always looking for the future in silicon chips and complex algorithms, right? But what if the next great leap in computing isn't something we invent, but something we discover? Something that's been hiding in plain sight this whole time, in nature's strangest and most beautiful designs.